Charles' Law, problems 1, 2, and 6 examples. So Charles' Law, as you can see, we have pressure, volume, and temperature. So Charles' Law is holding pressure constant, meaning there is no change in pressure, it remains the same. This is the way I like to represent the formula, but this is the way you may see it in Google or in a textbook. I find this easier to use mathematically. Feel free to use either one, but either way you need to show your generic formula. Okay, so here we are. Calculate the decrease in temperature when 2 liters at 20 degrees Celsius are compressed to 1 liter. Okay, so to use any laws in chemistry, basically any temperature in chemistry, we always convert it to Kelvin. So the formula to convert to Kelvin is to take Kelvin equals degrees Celsius plus 273.16. So 20 degrees Celsius plus 273.16 is 293.16 Kelvin. My formula is V1T2 equals V2T1. That's not a mistake. Temperature is always the opposite subscript as the P or V it's next to. And since P is constant, it's only next to V. So be careful where you plug your temperatures. Those are the temperatures is what gets my students making mistakes. You have to be very careful. Remember, you need the generic formula. And so then I know it's 2.00 liters times T2 equals 1.00 liters times 293.12 Kelvin. So look, I was very careful. I plugged T1 here because this temperature occurs with this volume. So they're both my 1s. I made that my 2. Again, what do I have 2 of? I have 2 volumes. They have to be in the same unit they are. If they weren't, I would convert. So I'm going to take and multiply these two and divide by 2 over. When I divide by 2 liters over, liters cancel unit-wise, leaving me 147 Kelvin. So 147 mathematically, and K, Kelvin, was the only unit left. In this problem, we have 600 milliliters at 20 degrees Celsius. What is the volume when it's 60 degrees Celsius? So we got to convert both of them into Kelvin. Remember, every temperature must be converted into Kelvin. No options here. So I got 393.16, and this technically should be 2 sig figs wise, but either way would work. And so then I'm going to plug in 600 milliliters and 333.2 for my T2. Remember, T2, temperature doesn't like to play nicely with others, so it's always the opposite subscript of the ones it's next to. V2 times 293.2 Kelvin, multiply the left, divide by the temperature on the right. So mathematically, remember 2 temperatures, they both are in Kelvin. When I divide it over unit-wise, Kelvin cancels, leaving me only milliliters. Mathematically, when I multiply these two, 600 and 333.2, hit equals, divide by 293.2, I get 81.87 milliliters. And example 6 is the last one we're going to do in this set together. A gas at 1 liter at standard temperature. Standard temperature is another way, like standard pressure, of giving you a unit or a number without giving you a value. So if you see standard temperature, you know it's 273.16 Kelvin. What is the volume at 333 degrees Celsius? Got to convert that Celsius into Kelvin. I did that here. And then remember the formula is V1T2 equals V2T1. 1 liter times 606.2 Kelvin. Why? Because T2 has to be here. V1T2 equals V2T1. Again, 2 things I have are temperature. Both of them are in kelvins. When I mathematically divide my temperature over, my unit of Kelvin cancels, leaving me liters for my unit and leaving me 2.22 liters for my mathematical answer. Now, let's see gas laws. If the temperature goes up on a gas, it's going to speed up and spread out. So then we expect to see an increase in temperature and an increase in volume. So they are what we call directly related. Let's see if we're able to show that mathematically. So here we see volume going down, so we should see temperature also going down. So remember, we went from 293 to 147. So they are directly related. They both did the same thing. Let's look at example 2. We have 20 degrees Celsius to 60 degrees Celsius, so temperature went up. Volume should also go. So you saw me pause the video probably there. What I realized is that I know that they are directly related. And when I started to go over this relationship with this problem, I saw that my temperature went up, but my volume did not. So I must have copied and pasted the answer wrong. So go back to number 2 and fix your math there. Sorry about that if I confused you. This is the correct mathematical answer, which we do see an increase in volume. So it's kind of nice because understanding these relationships can be a little bit of a self-check to make sure you didn't do anything funky. Again, 600 times 333. So just to double check what I'm saying, 600 times 333.2 equals, divide by 293.2. Should have been 681.8553888. So 681.9 milliliters. So that first answer, the 81 answer, was a mistake that I must have copied and pasted when I was building these notes. So correct that for example 2, please. Then looking at example 6, looking at that relationship again, We do see a increase in temperature, so we should see an increase in volume when we do, because volume and temperature are directly related.